Hi everyone, this is Sai Kiran. In this video, we are going to learn about the transformers architecture used in NLP models. By the end of video, I make sure that you have a clear idea and understanding of these core concepts. So, before going to transformers, uh, let's forget a transformer for a moment. So imagine this sentence. I ate a food because I was hungry. So here my question is like, what does I is refers to and what does because is connected to? As a humans, uh, so we look at the entire sentence at a once, understand the relation between the words. So, but computers don't understand these languages naturally. So in always we use a models like before transformers we use rnn lstm etc. So this reads sentence by word to word, uh, uh, like before that sentence we taken like I ate a food because I was hungry. It's like reads I at one and next is ate and next is food and because is next. So here problem is like that it is a slow and forgets earlier words and hard it's hard to train these models bad with a long sentences. So reaches so uh, researchers are like decided to invent a new thing. So here the model reads that like can a model read the whole sentence at a once like a humans? This question leads to the transformers. So before before starting about, I will share my screen and show my PPT. So now let's discuss about what is a transformer. So what is a transformer architecture? It's like a transformer is like a deep learning model mainly used in natural programming. Let me like it's used for translation English to French. Like transformer architecture is known as chatbots, ChatGPT. It used it for text summarization and question answering. So why that so let's discuss about why transformers were needed. So before going to transformers, we learn about what is RNN and LMTS. So basically RNN is like stands for recurrent neural networks. So it is designed to work with a sequences like a sentences. So example as we discussed before. So I love machine learning. Here RNN reads the sentence one word at a time. So first it reads I, then love, then then it reads a mission. Uh, then it's a learning. So our key idea is like to RNN is a small memory and has a hidden state can carries information from previous words. Uh, so think RNN is like a person reading a sentence word by word, trying to remember what was read earlier. So problems are with an RNN is like it has a two big problems. So first, it's like a forgets a long information. When sentence is longer, RNN starts forgetting that earlier words. So example, take like I grew up in a France, therefore I speak fluent. RNN may forget its a, like a word France. This is called long-term dependency problem. The next problem is like it's a slow. RNN processes words one by one, so trains it's a slow. Coming to LSTM, LSTM stands for long short-term memory. It's improves version. It is like improved version of a RNN. So LSTM was created to remember important information for a longer time. So LSTM uses to gates to decide what remembers and what to forget. So like a smart filters, it keeps important information only. So still, LSTM is not enough for the users. So even though LSTM is better than RNN, so still has a problems. So it still reads the words one by one. It's a still slow process. Still struggles with longer sentences. Harder to use a parallel processing. So we need a model uh, does to read a word by word and can look at a whole sentence at a once and remembers a long range relationships. So that's why transformers were introduced. So problem with RNN and LSTSS are I mentioned like sequence processing. It means slow training, long-term dependency problems. It's forgets a earlier what he'd written. It's difficulty to parallelize, so struggles with the long sentences. So all these problems are solved by using transformers. So transformers are used for self-attention instead of recurrence, process the entire sentence at once, faster and more accurate, and handles the long-range dependencies well. Moving to next slide. So here is the high-level architecture. So the transformer has two main blocks. It has input is for encoder and decoder is output. Encoder is to understand the input sentences. Decoder is generates the output sentences. Here, small example is like for we take here translation purpose. Input we given it's like I love machine learning as input, and it translates to French and gives these sentences. So encoder is used for understanding purposes and decoder it speaks the output. So core idea of a transformers is every words looks at every other words and decides what matters. So here is the self attention. This is called as a self attention. That's everything else exists support this idea. So let's learn about what is self attention. So the animal didn't cross the road because it was tired. So can I know what does it refers to here? So a transformer here a transformer looks at all words, assign the importance scores, and then learns. It is refers to a animal here. It's not a road. So each word asks who should I pay attention next. So self-attention is allows a model to connect it with the animal. So next moving to next slide. So next, how does a word look at other words? So computers can't look this. So the computers use the numbers. So each word becomes a vector here. The is vector is nothing but a list of numbers. So from each word of vector, we create a three versions. First is query. Query is used what is searching for, and key is what can I offer, and value is for actual information. Think it's like a Google search. Query is means we are searching in a Google, and key is like a web page title what we are giving. Then value is like a what the Google search is given the content. So for this we have a some formula just to remember. It's like attention is QKV equal to soft max QKT power 3 and root of dk into V. So here dot product of Q and K is similarity score, and scale by root of dk is stabilizing gradients, and apply softmax is like attention of weights. So multiply with V means it's a final output. So output is nothing but it's here weighted of some values. Moving to next slide. So here we are learning like attention calculations. For each word, it compares with a query and it with all the keys. So get a similarity scores, and it convert a scores to percentages of a softmax. So it uses this a percentages to a mix of a values. So here we get a result like a word representation that includes a context. So think about like bank near money is not equal to bank near river. So here next we are learning why multiple head is of attention. Humans don't focus on one thing only. We'll So what is mean by multi-head attention? So let's think about a human. Human don't focus on one thing only at a time. So like we look at meaning of a sentence, grammar of the sentence, position, relationships. So transformer does the same using this multiple head attention. Multiple attention heads, each head learns a something different, then combines all of them. So next move to next slide. So moving to next topic, what does word order? So here we taken a two sentences like dog bites a man, man bites a dog. So can I know if is these two sentences name is meaning is same? So absolutely no, no. So it has same words, but it has a different meanings. So here problem is that transformers don't know the order. So transformers handle this using this positional encoding. So let's learn about a positional encoding. We add a positional information to a word of vectors, so the model knows that what to give first word and what to give the next word. So and next word, the third word, etc. So encoder and decoder. Encoder is nothing but reads a input and understand its meaning. So decoder is like generates a output and predicts a next word step by step. Here, example is like encoder understand a sentences and decoder is to create a responses. Moving to next slide. So before going to encoder and decoders, we must look at a basic fundamentals. Four fundamentals. So here is first is word to numbers, or like it's word to vector and its embeddings. So second one is like positional encoding. It's like ordering of the QKV attention ingredients and similarity and relevance, how tokens inflow and out. So first discuss about word to number. Word to number is like word to vector and embeddings. So computer can't understand our words. It's take like example, take a cat. Uh, for C, it's a embedding is like 0.1 minus 0.56 and 1.34. This vector is called as a embeddings. So word to vector, it's like a idea, not a transforming specifics. So it learns a word meaning from its content. So learns word meaning from a content. So words is used for similar contexts. It's like a similar vectors. Example, king. It means it's like a man and woman. So it's king. It gives a queen. So transformers don't use word to vector directly, but they use the same idea. So it's like embedding that capturing the meanings. So moving to next slide, let's discuss the second one is positional encoding. So as we know, we discussed earlier, the transformers don't know the order. Here we take a sentence like I love you and you love I. So same words, but it has different meaning and different embedding and not a same words but same meaning, not a same embeddings. So here solution is we add a positional information. So final output is equal to word embedding plus positional encoding. We use sine and cosine here. So it allows model to learn a relative distance. So it generalize that longer sentences like conceptually here the token one is taken to know the first one and token 2 is taken to the knows the second one. Without positional encodings, the transformer we can think like it's a blind to word order. So moving to next one, QKV. As we discussed, each token creates a three vectors. First one is a query. As we know, this query means what I am looking for. It's like with Google search. And key is like what do I offer? And value is like what is my actual information. So all come from a same input from of embeddings using a different weights of matrices. So Q equal to X into WQ, K equal to X into W. Here W is mentions that weight of matrices and V is X into WV. So coming to fourth one, it's like similarity and relevance. So here is the take a sentence like an animal didn't cross the road because it was tired. So focus token is here. It is it. So let's discuss step by step of attention. Take a query of a it. So comparing with a key of all the tokens. So compute the similarities. Similarity is nothing but Q into K. High score equal to more relevant. So then softmax is nothing but converts a score to the probabilities, means like positional encodings. So example of attentions is like animal has 0.65 percentage, and road has 0.10 percentages, and tired is 0.20%, and others is like 0.05 percentage. So final representation of it has 0.6 has animal into V percent, 10% of road, and 20% of ride. So this is how token relevance happens. So here finally it refers to higher weight. We have that here percentage is 0.5. It's here it refers to a animal here. So moving to next slide. So how this affects a general text? When we generating a text like token with a higher attention weight, so it influence like a next word predictions more. Example, take a prompt like uh, what is the capital of France? So France has a higher relevance, so next token is like a Paris. If attention is wrong, its model produces a wrong answers, like it's hallucinated answers. So moving to next topic, sequence to sequence. So we'll discuss why encoder and decoder exist here. So sequence to sequence is like input sequence to output sequence. Example, we can take it like for transformer example. We use for translation means language to language, English to Telugu, English to France, English to Tamil. We use for summarizations, we use for question answerings, we use for problem solvings. Like we give the input and it gives a output. The length is differences. Output depends on the entirely depends on input what we given, and transformer solved by this using encoder and decoder architectures. So moving to next slide, we will discuss about encoder only transformer. Uh, Encoder only transformer. So I will first we will discuss in a similar simple explanation. So encoder is only transformer or models that use for only encoder part. This is like a transfer part of a transformer architecture. Uh, so mainly the encoder does is uh, job is to read and understand the text of an input. So encoder is only the models are not used for generating a new text. So they are used to understand the text of input text deeply. So uh, what does do? I think you get an idea like understanding text means it's like nothing but finding a meaning, understanding the content, like knowing the relationship between the words. Let's take an example like the word bank in deposit money. The bank in the river bank has a different meanings. So encoder only model to understand this the difference between the sentences. So some well-known encoders are only models are like uh, some models are like BERT. BERT is not nothing means it's a bidirectional encoder representations for your transformers, and like Roberto is like it's like a improved version of BERT. So distill BERT is like a smaller and faster BERT. So Albert coming to next. Albert is like lightweight and memory efficient BERT. So all these variations are the same, but idea is to strong text understandings. So moving to next, what are the used for? So encoders only models are the best to understand a task. So here we take a task like test classification means spam detection. Sentiment analysis means position may position are positive or negative. So name identity recognizer means name and place of a company. Question answering here example is like finding the answer of a text. Uh, Semantic similarity means meaning comparison between the sentences. So coming to next slide. Now we will discuss encoder, how internally works. First we will take a first we will take as a tokenization. So we'll take a lesson, the sentence like I love machine learning. It becomes I love machine learning, different words. Bird uses a word piece and tokenization. So next, step two, it has embeddings. Embeddings, basically we have a three types. Encoders only models has a three embedding models: the embedding type and purpose of a type. So token embedding is like word meaning. Positional embeddings is like used for word order, and segment embedding means sentence A or B. So finally, our input is like input equal to token plus position and segment. So moving to next slide, bidirectional self-attention. So encoder only transformers are like used for bidirectional self-attention. Meanings of like meaning. So bidirectional is nothing but it's a self-attention of encoder-only transformers. It's used for bidirectional attention, meaning of each word looks at both left and right context. So let's take example here. I went to the bank to deposit a money. So like take another example, like I sat on the bank of the river. So bank attempts to deposit and money. So here is a financial bank. A reverse indicates that river bank. This is why bird understand the meaning deeply. So coming to next step, it's like QKV in a encoders only models. So it has the same mechanism as a encoder in a full transformer. So for each token, we have like Q equal to X into WQ, K equal to X into WK, V equal to X into WV. So let's discuss about multi-head attention. As we discussed before, multi-type attention means heads only. It's like allows a model to focus on a different types of relationships at the same time. So some heads learns the syntaxes, semantics, conferences, long-range dependencies. So moving to next step, it's like a staked encoder models. It's a like 12 bit basic and 24 bit is like a large. So each layer refines a understanding. So output is like context and aware of vector per token. So coming to next, it's like a staked encoder layers. Usually it has a 12 bit base and 24 bit it's a log. So each layer refines its understanding. So we get an output like context aware vector per token. So coming to next slide, uh, It's like a masked language modeling. It's where MLM. It's nothing but encoders only models are trained by hiding some words, and asking a models that to predict them. So here, like take an example is I love mask learning. So like mask is nothing but we can think of it like missing word. So model predicts the mission and why this works. So forces to understand a full context and uses left and right words. So coming to next step, it's like next step, next sentence prediction. It's a bird. It's like the model is used to train and understand the sentence relationships. Uh, like combining the let's take an example of paragraph. We have different set of words, different set of sentences. Uh, to understand that relations, it you the next sentence of prediction is used. So example, here take a sentence as I went home. So sentence B is like that. So prediction is B is a next and sentence of A. B is next to sentence of A. So moving to next slide. What does the model output? So encoder only model output is like one vector per token. So it's like special class token. Encoder only models are has a special class token CLS. It's like a for beginning we use. So special class token is nothing but it's like a here CLS is token. It represents the meaning of the entire sentence. So it's like if each word has a vector like a paragraph summary, so its CLS is like a vectors. It's a full document. It shows a full documented summary. So example of here CLS is like nothing but it's like a sentence meaning, input sentence meaning. So let's talk how tasks are done. So let's take a classification. CLS is a vector. So add a classifier layer. So question for it use it for question answering, predict and start, predict start and a token. So similarity is like to comparing the embeddings. So before going to decoder, let's summarize the encoder. So it's like uh, by the encoder, we learn like it's like only a transformers. It uses for self attention to understand the text by allowing each word to attend every other word in both the direction and left and by right directions. So they are trained using a masked language modeling and are ideal for understanding basic tasks like classification and question answerings. So that's all about the encoders. In next video, we'll discuss about how decoders works. Thank you. Thank you for your time.